a non-empty subset G equipped with a binary operation. We know what do you mean by binary operation. We know that G cross G contains set of elements of the form AB such that A comma B belongs to G. Any mapping F from G cross G to G is called a binary binary operation on G. F from G cross G to G is a binary operation on G. That means, and we denote a binary operation by either star or circle. Or we say that star is a binary composition. If A star B belongs to G, for every A comma B belongs to G. And we know how to prove the associative property, identity property, and inverse property. We say that the binary composition star is associative if A star B star C is equal to A star B star C for every A comma B comma C belongs to G. And there exists an element E star belongs to G such that A star E equal to E star A equal to A for every A belongs to G. And for every element A belongs to G, if there exists B in G such that A star B equal to B star A equal to E, then we say that B is the inverse of A. B is the inverse of A or A is the inverse of B. We say that this G along with this binary composition is a group with the respect to star with these three properties. G star is a group with respect to star. If a star is associative, there exists an element E belongs to G such that A star E equal to E star A equal to A for every A belongs to G. And also for every A belongs to G, if there exists B belongs to G such that A star B equal to B star A equal to E, then we say that G star is a group with respect to the binary composition star. In addition to this, if A star B equal to B star A for every A comma B belongs to G, then we say that G is commutative. Commutative group or an abelian group. And we have in earlier sections or earlier classes in algebra, we have learned when G is a group. And we have seen many examples of a group. And we say that a non-empty set H is a subgroup of G. A non-empty subset, a non-empty subset H of group G is said to be a subgroup of G if H itself is a group. That means, and also we proved when this H is a subgroup of G. We know that whenever H is a subgroup of G, whenever H is a subgroup of G, then we have H inverse is equal to H and H is equal to H. All these points which are we are going to use in commutative algebra also. H is a subgroup of G, then H inverse is equal to H and H into H is equal to H. And in general, we prove that or we know that H is a subgroup of G if and only if A comma B belongs to H implies AB inverse belongs to H. And we know that the union of two subgroups need not be a subgroup of G, whereas intersection of any two subgroups is again a group. Intersection of any two subgroups is again a group. See, and also if H1 is a subgroup, H2 is a subgroup of G, then H1 union H2 is a subgroup of G if and only if either H1 is contained in H2 or H2 is contained in H1. Either H1 is contained in H2 or H2 is contained in H1. Now we say that H is a normal subgroup. H is a normal subgroup of G if for X belongs to G, H belongs to H, we have XH, X inverse belongs to H, then we say that H is a normal in G. And see here, the product of any two subgroups is a subgroup. Intersection of subgroups is always subgroup. Why intersection of subgroups is always a subgroup? Whenever H1 is a subgroup, we have AB inverse belongs to H1. And H2 is a subgroup, means AB inverse belongs to H2. Then you have AB inverse belongs to H1 intersection H2. So you have H1 intersection H2 is a subgroup of G. Now here, at the same time, you have if X belongs to G and H belongs to H1 intersection H2, then definitely XH X inverse belongs to H1 intersection H2. Therefore, you have intersection of any two normal subgroups is also a normal subgroup. Generally, what is the advantage of studying this algebra is here, algebra and analysis, they polish your brain like anything. So just to improve your analytical skills and problem solving skills, we have to learn this algebra and analysis also. Now here we have defined, we have started with a non-empty set G, and we have taken elements of G in pairs, and we have defined a binary operation on G, and we have seen what are the properties of binary operation. One is associative property, the second one is identity property, third one is inverse property. So any non-empty set along with the binary operation star, which satisfies the properties of associativity, identity, and inverse, is called a group. Now we can have many properties of groups, like in a group, identity element is always unique. In a group G, the identity element is always unique, and also inverse of every element is also unique. There exists one and only one inverse for each and every element in a group G. And we have seen several examples of a group. And then subgroup. Coming to subgroup, when do you say that a non-empty subset is a subgroup? A non-empty subset is a subgroup only when it itself is a group. So we say that H is a subgroup of G when H is a subset of G and H itself is a group. H itself satisfies properties of all groups. Then we will study a separate kind of subgroups called normal subgroups. When do you say that H is a normal subgroup of G? For every X belongs to G, H belongs to H. If you have XH X inverse belongs to H, then we say that H is a normal subgroup. So here intersection of any two normal subgroups is a subgroup. Then after that, we define coset. What do you mean by coset? Yeah, A is a fixed element of G. A is a fixed element of G. We say that HA, the set of all HA such that H belongs to H, is called a right coset of H in G. And AH is the set of all AH such that H belongs to H is called a left coset. It is called a left coset of H in G. Here, generally, if H clearly from the definition, because E belongs to identity element, E is the identity element which is common to both the group and subgroup. You can write A can be written as AE, so which belongs to AH. Similarly, A also can be written as EA, which belongs to HA. That means you have whatever the cosets, either left coset or right coset, you have defined. They are non-empty sets. Now, clearly, A belongs to AH, A belongs to HA. Now, generally, you have H belongs to G means we can talk about capital H into small h into capital H. This is the right coset, this is a left coset. Now, if this H is element of H, if H belongs to H, then you have HH is equal to small h into capital H is H. That means if whenever H is an element of H, there is no distinction between a left coset and a right coset. That means H into H is equal to small h into capital H is H. There is no distinction between a left coset and right coset. Suppose if whenever H is a normal in G, we have if H is a normal subgroup of G, if and only if XH X inverse is equal to H. Because whenever you are saying that XH X inverse is the subset of H, means you have X capital H X inverse is the subset of H. This happens for every X belongs to G. For every X belongs to G, if XH X inverse XH X inverse is equal to H. Or we say that, what do you mean? This is if and only if XH X inverse X equal to HX or XH is equal to HX. Therefore, H is normal in G means you have every left coset. Every left coset is also a right coset. Now, the advantage of the main aim of studying or learning algebra is to study the similarities between dissimilar objects. So, for this, we make use of a function. Generally, we know what do you mean by one function and onto function. We say that a function is one if and only if distinct elements in A has distinct images in B. That is, suppose f from A to B is a function. F is said to be 1 F is 1 if f of A1 equal to f of A2 implies A1 equal to A2. And for every B belongs to B, if there exists A belongs to capital A such that f of A is equal to B, then we say that means f is onto. That means if f of A is equal to B, that means for every element B, there exists a pre-image in capital A. In such case, we say that f of A equal to B, or we say that means we know whenever f from A to B is a function, f of A is a subset of B. So for every B belongs to B, there exists A belongs to A such that f of A equal to B means f is onto function. Students, you are all have to have an idea on sets, their properties, groups, ideals, subgroups, normal subgroups. Otherwise, commutative algebra is a little bit higher level of this algebra. So if you want to learn perfectly this commutative algebra, be perfect with the concepts of sets and functions. So we say that function f is onto whenever there exists a pre-image. There exists a pre-image for each and every element in the range. Or in other words, the number of elements in set A is equal to number of elements in set B. Then we say that the function is onto. Next one, we are going to study special kind of functions called homomorphism. What do you mean by homomorphism? Suppose f from G to G dash is a mapping. Here G is a group with respect to star and G dash is a group with respect to circle. Suppose if f is a mapping from G comma star to G dash comma 0, and we say that f is a homomorphism if f preserves the binary operation. F preserves the binary operation. That is f of A star B is equal to f of A circle f of B. Generally, while defining the definitions, we go for multiplication as a binary operation, or we say that f is a homomorphism if f of AB is equal to f of A into f of B. So a homomorphism, one is called monomorphism. A homomorphism onto is called endomorphism, and monomorphism, endomorphism, and epimorphisms are onto homomorphisms. Endomorphism is a homomorphism from a group G onto itself. Now next one is isomorphism. What is an isomorphism? Isomorphism is a 1-1 and onto mapping. A 1-1 onto and a homomorphism. A 1-1 onto mapping is called a isomorphism if f is a homomorphism. That means we say that the mapping f is an isomorphism if f is 1-1, f is 1 onto, and f is a homomorphism. Then what do you mean by epimorphism? Epimorphism is onto homomorphism. And suppose you have f is a mapping from group G onto itself and an isomorphism. An isomorphism from G to G is called automorphism. without the properties of these homomorphisms and all, we cannot do 9 lemma. There are several important theorems in commutative algebra which will make use of these homomorphisms, automorphisms, endomorphisms, and epimorphisms. Now, after defining homomorphism, you have to define an important property of homomorphism is called the kernel. Kernel of homomorphism F is the set of all elements of G that are mapped onto identity element of G dash, where here the set of all x belongs to G such that f of x equal to E dash, where E dash is the identity element of G dash. Kernel of F. Kernel of F is the set of all those elements which are mapped onto identity element E dash of the group G dash. And clearly, we know that kernel is a normal subgroup of G. Kernel is a normal subgroup of G. Why? Because after defining homomorphism, we know that f of A inverse is equal to f of A whole inverse. And you have f of E is equal to E dash, and f of A power n is equal to f of A whole power n. Keeping these concepts in our mind, we prove that f of A, B is we prove that kernel is kernel. Generally, we denote ker f or K is the set of all x belongs to G such that f of x equal to E dash, where E dash is the identity element of G dash, is called, okay, this is a normal subgroup of G. Why? Because if you take f of AB inverse, what is f of AB inverse? It is f of A into f of B inverse, which is nothing but f of A into f of B whole inverse. That is f of A is E dash, because whenever A comma B belongs to K, we have f of A is equal to E dash, f of B equal to E dash. So f of AB inverse is E dash. Hello, Chippu. ఓకే, నారాయణ సిల్క్స్ బాగున్నాయని చెప్పారు, మా కొలీగ్స్ కొనుక్కున్నారు. కొంపల్లిలో ఉంది, వాళ్ళదే కొంపల్లి బ్రాంచ్ బంజారా హిల్స్ లో ఉంది అది. Hello. So F is 1 onto and homomorphism. Now we prove fundamental theorem. Just we don't prove, just we will state fundamental theorem on homomorphisms. Every homomorphic image, every homomorphic image of a group G is isomorphic to quotient group. Every homomorphic image of group G is isomorphic to a quotient group. Now, what do you mean by quotient group? If you take G by H, it is set of all cosets such that A belongs to G. Then we define multiplication of two cosets, HA into HB is equal to HAB. Because whenever A comma B belongs to G, by closure property, you have AB belongs to G. Therefore, you have HAB belongs to G by H. Now, you have HA into HB into HC is HA into HBC or HA into BC, which is HABC, which is HA into HB into HC. So coset multiplication also satisfy associative property. Coset multiplication will also satisfy associative property. Now, you have HA into HE is HAE, which is HA. And HE into HA is HEA, which is HA. That means you have, we know that hello? Chappu. Okay. So we prove that we prove the fundamental theorem of homomorphism, that is G by K is isomorphic to G dash, that is G by K is equal to Ka such that A belongs to G. Define phi from G by K to G dash such that phi of Ka is equal to f of A. Because you have, if A belongs to G, then Ka belongs to G by K and f of A belongs to G dash. Why? Because f from G to G dash is a homomorphism. Then only we say that f of G is homomorphic image. Here f from G to G dash is a homomorphism. Then you have G dash is said to be homomorphic image. So every homomorphic image is isomorphic to some quotient group. So for that we have taken here kernel, where K is kernel. K is kernel means the set of all x belongs to G such that f of x equal to E dash. K is a kernel, and we know that kernel is a normal subgroup of G. Kernel is a normal subgroup of G. So, and also you have Ka equal to Kb. That means from the cosets we know HA equal to HB if and only if AB inverse belongs to K. So you have AB inverse belongs to K. What do you mean by AB inverse belongs to K? F of AB inverse is equal to E dash, which implies F of A into F of B inverse is equal to E dash. Or you have F of A into F of B inverse into F of B is equal to F of B, or which implies F of A equal to F of B. This implies phi of Ka equal to phi of Ka equal to phi of Kb. So the function phi we have defined is well defined. Phi of Ka equal to f of A function is well defined. Now you have phi of Ka equal to Kb, or phi of Ka equal to phi of Kb implies f of A equal to f of B, or which implies f of A into f of B inverse is equal to f of B into f of B inverse, which implies f of A into f of B inverse is E dash, which implies f of AB inverse is E dash, or you have f of A into, or f of B inverse is E dash means AB inverse belongs to K, which implies Ka equal to Kb. That is, whenever phi of Ka equal to phi of Kb implies Ka equal to Kb, your phi is 1, 1. Ka equal phi is 1, 1. Similarly, phi is on 2, and phi is homomorphism, since phi of Ka into Kb is phi of Kab, which implies f of AB, which equal to, which is f of A into f of B, which is phi of Ka into phi of Kb. So phi is a homomorphism. Hence phi is a 1, 1 onto homomorphism. Hence it is an isomorphism. Students, try to learn the simple theorems. Let us build the concepts from the basics. So from the groups, what do you mean by a group? A binary operation equipped, a non-empty set equipped with binary composition is said to be a group. If binary composition satisfies the properties of associativity, identity, and inverse, and then F is said to be, G is said to be a abelian group, if it satisfies commutative property also. So read the properties of subgroups, normal subgroups, homomorphisms, and isomorphisms, and normal subgroups. If you know all these, then it is for you only easy to learn the commutative algebra. After that, next one is ring. Ring. What do you mean by a ring? We say that a non-empty set R, we say that R plus dot is a ring. If first one, today is an introduction class, that is the reason I am explaining only the basic concepts. From next week onwards, we are going to enter into the syllabus. If R plus is an abelian group, second one, R dot is a semi-group, and third one, distributive laws are satisfied. That is A into B plus C is A into B plus A into C. And fourth one, or B plus C into A is equal to B into A plus C into A. A non-empty set R plus dot, a non-empty set equipped with the two binary compositions is called a ring if R plus is an abelian group, R dot is a semi-group, and the distributive laws are satisfied. Okay, so we say that multiplication is also commutative. R dot and addition is R plus, means R is a group with respect to addition. Multiplication is a semi-group, means what is a semi-group? A binary composition. Dot is a binary composition which satisfies associative property. So R is in R, multiplication is associative. Now R dot is a semi-group. If with respect to multiplication, R satisfies commutative property also, that is A into B equal to B into A, then we say that R is commutative. Okay, now? So we say that R is a commutative ring with unity if their exits 1 belongs to R such that A into 1 is equal to 1 into A equal to A for every A belongs to R. So it is R is a ring with unity. And see here, R is a commutative ring with unity if it satisfies commutative property and this one, and identity property, that is there exists a multiplicative identity 1 such that A into 1 is equal to 1 into A equal to A. Hello? Hello. So this is a commutative ring with unity. With respect to multiplication, each non-zero element for every a not equal to 0, if you have a into, there exists b, such that ab into ba equal to 1, we say that a is the multiplicative inverse of, or b is the multiplicative inverse of a, or a is the multiplicative inverse of b. So in a commutative ring with unity, if each non-zero element possesses multiplicative inverse, we say that r plus dot is a field. A commutative ring with unity in which each non-zero element possesses multiplicative inverse is said to be a field. So we say that r plus dot is a field. So students, next week we are going to learn some more properties.